The cause of the movement and rate of acceleration, deceleration of discrete solid objects in fluid mediums. Density is defined as the mass per unit volume. Density is an intensive property of a pure substance, which means no matter how much you have of the substance, the density will always be the same. Whether you have 1 liter or 10 liters of water, the density of both volumes of water will be the same. Density is mathematically defined as mass divided by volume. The density of a substance is the total mass of that substance divided by the total volume occupied by that substance. The relative density of substances and how substances are observed positioned relative to each other. A number of other factors must be taken into account. Liquids and gases are fluids and hence flow. Solids do not. The state of matter of substance at a specific temperature will influence its position relative to another substance. The type and strength of attractive forces between the particles of a substance compared to another substance will influence the position of the two substances relative to one another. This topic has a number of possible situations, each needing its own definition to avoid confusion. These definitions are based on a discrete solid object being in a fluid medium. A discrete solid object will be taken as an object with a definite volume and shape, with component particles close together and fixed into place. A fluid medium will be taken as a liquid, mixture of liquids, a gas, or a mixture of gases. A discrete solid object that is suspended in a pure fluid medium is in relative density equilibrium with the same pure fluid medium. This is because the discrete solid object and the pure fluid medium have the same densities as each other. Pure, as in consisting of only one substance. A discrete solid object that is suspended in a heterogeneous fluid medium solution is in relative density equilibrium with a certain section of the heterogeneous fluid medium solution. This is because the discrete solid object and that certain section of the pure fluid medium have the same densities as each other. Relative density equilibrium arrest. A discrete solid object that is being prevented from moving through a relatively more or less dense fluid medium it is in by an external agent is termed as being in relative density equilibrium arrest. The man has picked the keys off the floor and is holding them above the floor. The keys are surrounded by the fluid medium of air. The keys are in relative density equilibrium arrest. The helium balloon is stuck in the branches. The helium balloon is surrounded by the fluid medium of air. The helium balloon is in relative density equilibrium arrest. It is the action and subsequent discontinuation of action or non-continued action of the external agent that causes the movement and direction of the discrete solid object through its fluid medium surroundings. But it is the density of the discrete solid object relative to the density of the fluid medium that it is moving through that will determine the rate of acceleration or deceleration of the discrete solid object. It has been shown that it is the action and subsequent discontinuation of action or non-continued action of the external agent that causes the movement and direction of the discrete solid object through its fluid medium surroundings. Cause, action or discontinuation of action by the external agent. Effect, moving object away from or towards the ground. Reversely, no cause equals no effect. No external agent equals object doesn't move away from or towards the ground. Final summary. It has been shown that it is the action and subsequent discontinuation of action or non-continued action of the external agent that causes the movement and direction of the discrete solid object through its fluid medium surroundings. The density of the discrete solid object relative to the density of the fluid medium causes the rate of acceleration, deceleration of the discrete solid object through the fluid medium. There is no contradiction or mismatch between what has been proven and validated by the scientific method and Newton's laws of motion.
First, we will observe the magnetic field when the magnets are all lined up and coherent. As you can see, the more magnets we align pole to pole, the stronger the magnetic field gets. However, this is the complete opposite when the poles are not aligned. As you can see, the more magnets we add to our incoherent mass, the weaker the magnetic field gets. Now let's take a look at how a coherent object, the cylinder magnet, interacts with the large incoherent mass of magnets and ball bearings. As you can see, the red pole of the magnet is attracted to the mass, so we might assume that the bare pole of the magnet would repel. Yet this is not the case. As I flip the magnet over, the bare end is also attracted to the mass. So how does this relate to what we are calling gravity? Like gravity, incoherent magnetism is an attractive-only force. No matter which pole of the magnet is placed near it, the incoherent magnetic field is always attracted and never repelled. All matter is made up of charged particles, and like magnets, these particles have poles. The Earth and everything on it is ultimately a huge mass of charged particles. This is why everything is attracted towards the Earth. There are a few apparent exceptions to this rule, like helium, balloons, and rain clouds. I will try in this video to explain how incoherent electrostatic acceleration works while using examples that can be recreated by anyone. To start out, we will take a look at Earth's electrostatic field. This is important because we, along with all the matter in this known realm, are inside of an electrostatic field. The Earth itself has a measurable negative charge compared to the air above it all across the plane. As soon as you leave the surface, there is a positive charge in the air around you that grows in electrostatic potential the further you go up towards the sky. It is a steady, gradual rise in potential, which tells us, according to the laws of electricity, that we are between two Gaussian surfaces. A Gaussian surface is simply a surface that encloses or distributes a charge. If there were only one surface, the rate at which the positive potential grew would be different. Knowing that we are between two Gaussian surfaces, we can also know that certain phenomenon will take place in all matter within the electric field, or area between the two surfaces. For this topic, we will first look at polarization through electrostatic induction. Electrostatic induction is a phenomenon where the positive and negative static charges on matter are slightly separated or polarized due to the electrostatic charge of its surrounding area. If one set of the object's surroundings is positive and the other negative, the negative charge on the object will be attracted to the positive area around it, while the positive charge on the object will be attracted to the negative area on the opposite side. So here on Earth, the positive charge on our bodies is always attracted down towards the Earth, and the negative will be attracted to the air above. This phenomena creates a slight force in that downward vector, because as soon as we leave the ground, we start becoming positively charged by the air around us and are now forced towards the negative of the ground. This is electrostatic acceleration. One might think that the attraction from above and below would cancel out completely, but it is the electrostatic gradient that creates a flow from the positive above to the negative below. Think of the Earth as a flat strainer, and there is a constant flow of water from above, moving very slowly, always applying a force in a downward direction. This would be considered a vector. The electrostatic potential difference getting stronger as you rise from the Earth will keep a steady pressure from above at all times until it reaches the Gaussian surface above. When we reverse the polarity of the electric field and put a negative surface above a positive one, we can reverse this electrostatic phenomenon and get things to stick to the upper plate as if it were the ground. This works with all types of matter.
Density and buoyancy is an expression of, it's like an effect that sets in when force is applied to matter. Then the matter starts rearranging itself within the body to which the force is applied in accordance to density and buoyancy in the form of pressure, in which also weight is expressed, by the way. And the density and buoyancy sets in accordance to the forces being applied. So if there is a motion upwards, an accelerating motion upwards to a body of matter, for example, things will be pushed down. If there's an accelerating motion sideways, then the heavy will be pushed in opposition to the direction it's going in, and the light will be pushed in the direction it's moving in. All these types of effects are very obvious. They are absolutely crystal clear. They are universal, and they always work. No.
If somebody claims acceleration happens, right, and in any given case, we can see that with gas and liquid, and any motion that we apply to it, we get displacement of the gas in the liquid. Now, if I was to hold this here and I was to let it go, right, people are invoking that this thing moves through space. Right? When I let that go, it's being claimed that this moves through space. So this is being claimed to accelerate, to move, motion. What have we established? If somebody claims motion happens, we need something that pushes on it. Right? No such thing as pull. Only push. Pressure makes stuff move. So if this was to be accelerated in any direction, we get displacement of the gas in the liquid. In reality, When I let this go, there is no displacement. So acceleration, if I accelerate it in that direction, the liquid moves to the back and the air towards the direction of acceleration. So here, if somebody's going to claim this accelerates downwards, then this moves to the top and the air should move to the bottom. That's what happens in the case of acceleration.
This means it is not true that no experiment can distinguish between a uniform gravitational field and acceleration. At last, we can establish a test for true motion. Here's how. If there exists some local switch we can find to make a gravitational field in our immediate vicinity instantaneously vanish, then we know that, in fact, this gravitational field cannot have been real, and that previously we had been undergoing true motion. In the case of the car, the switch is the accelerator pedal. In the case of the rocket, it's the firing of the rocket engines. Now, in a similar manner, let's ask, is there something we can do at the surface of the Earth to instantaneously switch off the gravitational field there? Because if we can indeed find such a switch, this will distinguish for us whether the force causing all objects to fall down is a real one, or rather, if it is merely an apparent one, caused by an erroneous judgment of motion from an accelerated frame of reference. It turns out there is such a switch. What is it exactly? Well, go to the top of a tall building and step off of it. The instant you step off the building, the gravitational field in your immediate vicinity instantaneously vanishes. You can prove this to yourself by performing the free body test for inertial motion as you fall. Just like the unaccelerated observer in the rocket ship, you will discover that, neglecting air resistance, if you toss objects off yourself while falling, these objects will float away with uniform motion. Carry a spring with you, it won't compress. Try to weigh yourself on a scale, and you'll get a reading of 0. According to Newton's laws, you therefore must conclude that your frame of reference is inertial, and that you are not accelerating. But if you aren't accelerating, this leaves one and only one logical possibility. It is the Earth that is accelerating towards you.
So we've got an object that's attached to Earth, and Earth's moving, right? Now the Earth's moving at its set rate, constant velocity, say, which would be, we'll say if we're talking say 1,000 miles per hour. So the Earth and this thing that's attached to it's moving 1,000 miles an hour. As soon as that's no longer attached to that, right, it's going to start a process of decelerating, it's going to get slower, right? And if it's no too far away from the surface of the moving reference frame, then as it comes off there's a slight impact, right? Slight impact, because it's not had a chance to decelerate, right? It's still moving relatively, you know, quickly in regards to the reference frame. It's not going to lose that much of its speed, right? I mean, these things are just basic physics. If I'm now standing up here, you know, again, we're looking at this as if we're vertical. Now if I'm standing up here and I'm holding this out here and I let it go, right, then it's going to start its deceleration process. It's going to get slower and slower and slower, and the Earth would come up and hit it harder, right, because it's got a bigger gap, there's more time for it to decelerate. If it's out here, you know, and it's just gone the same rate, right, like if I had a craft that was moving at the same rate, then that's what would happen. But when I step off of here or I drop something off of this, it begins a process of decelerating as this moves continually at its same speed. So as it's getting slower and slower, this is just going to come up and hit it with more impact. If you were witnessing that, it would give you the impression that this thing was getting faster and faster and faster.
As soon as I let go of my phone, there's not going to be any acceleration. It'll immediately drop to 0. Not when it reaches the top of the peak and then comes back down, but actually right when it leaves my hand. So you can see that long drop in acceleration there. That went exactly to 0 Gs as soon as it left my hands. So what that means is if you just throw something up in the air or just drop it, as long as there's nothing touching it, it'll just register 0 G, so it won't feel any downward pull on it. For example, the only reason that you feel like you're being weighted down and pulled down is because the ground is actually pushing up on you. If you didn't have a ground pushing up on you, then you wouldn't feel weighted down. Now, a little caveat to this is to remember that when you're falling on Earth, usually in the atmosphere, you're falling through air. And if you're falling through air, then that air is hitting you and it's pushing up on you a little bit. So you are actually feeling a little bit of gravity as the air is pushing on you. In fact, the interesting thing about air pushing up on you is when you reach your terminal velocity, when you're falling through the sky and you're not accelerating anymore, that's when you've reached your terminal velocity. Actually, the air is pushing up on you with as much force as you'd feel as if you were just laying on the ground. So you pretty much don't feel weightless anymore once you reach your terminal velocity. So when you fall out of the sky skydiving, you don't actually feel weightless.